Rainwater and groundwater differ in several important ways regarding purity, mineral content, infiltration, and long-term water sustainability. Here's a breakdown. 1. Purity. Rainwater. Generally purer when it first condenses and falls from the atmosphere. However, it can pick up airborne pollutants, e.g., sulfur dioxide, nitrogen oxides, particulate matter, making it slightly acidic, acid rain. When collected from surfaces like roofs, it can become contaminated with debris, bird droppings, and other pollutants. Groundwater. Typically cleaner biologically, fewer pathogens, due to natural filtration as it moves through soil and rock layers. However, it may contain dissolved minerals, sometimes excessive, like arsenic, fluoride, or iron, and is more vulnerable to chemical contamination from agriculture, industry, or leaking tanks. 2. Mineral content. Rainwater. Low in minerals, often considered soft water. Lacks essential minerals like calcium or magnesium unless it picks up dust or other particles during collection. Groundwater. Rich in minerals, especially in areas with limestone or other soluble rock types, often hard water containing high levels of calcium and magnesium. 3. Infiltration. Rainwater. The primary source of recharge for both surface water and groundwater. Its infiltration capacity depends on factors like soil type, vegetation, urban development, and rainfall intensity. Groundwater. Result of long-term infiltration of rainwater and surface water. Infiltration is slow, often taking months or years to reach aquifers, depending on soil rock permeability. 4. Contribution to long-term water sustainability. Rainwater. Short-term supply potential through rainwater harvesting systems. DTM. Useful for decentralized water management, reducing demand on municipal supplies. Groundwater. Critical for long-term water security, particularly in agriculture and areas without surface water. Over-extraction is a major concern. Recharge is slower than extraction in many areas, threatening sustainability. Feature rainwater, groundwater purity cleaner, initially but variable filtered, fewer pathogens, but risk of chemical contamination. Mineral content low, soft water, high, hard water. Infiltration, source of recharge, result of infiltration. Sustainability, good for short-term use, crucial for long-term supply, but vulnerable to overuse. Conclusion, both are essential in the water cycle, but sustainable water management depends on using rainwater for non-potable or supplementary uses, while preserving groundwater for critical long-term needs. Your concern is deeply insightful and highly relevant to the karst hydrology of the Texas Hill Country, especially near the Balcones Fault Zone, where the interplay between flash flooding, limestone dissolution, and geological instability, like sinkholes or subsidence, is critical. Here's a comprehensive breakdown of what can be done to capture flash floods without accelerating karst dissolution or risking catastrophic collapse. 1 is the loneliest number that you will ever know. Yes, it's the loneliest number you'll ever know. 2 can be as bad as 1, but the loneliest number is the number 1. The problem: flash flooding plus karst risk. In karst terrains, water moves quickly through fractures, sinkholes, and caves, often bypassing filtration and carrying acidic or high carbonate rainwater into soluble limestone, datra. This accelerates dissolution, enlarges subsurface voids, and increases the risk of sinkholes, especially near fault lines like the Balcones. Flash floods, due to their force and volume, can magnify this risk by 2. Strategy: capture, delay, and redirect without deep infiltration. 1. Surface retention with lined basins. Use clay-lined or geomembrane-lined retention basins to hold stormwater temporarily without allowing it to percolate directly into the limestone. This detains water and slows runoff without feeding it into karst conduits. Gradual release can be controlled toward evapotranspiration zones or constructed wetlands. 2. Engineered wetlands and vegetated swales. Build shallow vegetated swales that absorb some water into the soil root zone, rather than allowing deep infiltration. Plant deep-rooted native grasses and shrubs that draw water upwards and stabilize soil. Cisterns and modular capture tanks. Install above-ground or buried cistern systems that directly harvest floodwater from arroyos or flash channels. Use for non-potable reuse, irrigation, fire control, etc., reducing runoff and demand on groundwater. 4. Controlled discharge to surface streams. Divert excess stormwater to existing surface water channels, like creeks or ephemeral streams.